When I went to architecture school a few short years ago, we were very concerned about massing studies and about the visual form of a building on its external. It wasn't until many years later that I really learned through experience that how a building operates or how a building performs or how it makes people happy is really about the interior. And it's really about how the space is illuminated and how the space is configured as an internal experience. And so I became very focused on the human factor equation and primarily driven by visual experience. And so I focused my studies and my research, my career mostly on how do people perceive interior architecture and how does this really impact our experience. And so I've been working on a research project which is a little bit separate from my work that I've been doing in California, looking at the color experiences inside Buddhist temples. And from this research work, it actually helped me inform some of the design standards that I developed for the state economy in California. So today, what I'm going to do is I'm going to talk about this research project and how it's informed lighting standards in the United States. And so that's the main thrust of this morning. Before I get into the temples work, I wanted to do a little bit of background just in terms of some of the terminology that I'm going to be using. This terminology is very common in lighting design, interior architecture, and it's something that you folks will be working with in your future. And I call this really the metrics of color and light. And these are very standard kinds of design terms that get used in our industry. And I really want to sort of start talking about how do we experience color or light inside a space. And again, these are all concepts and fundamentals that you're all going to be dealing with in your future. So just in terms of a little bit of introduction, if you look at this interior, we would qualify this as a warm environment. And so if you had to describe this, you could simply describe this as a warm interior. In contrast, we would call this a cool interior. Okay, if you had to describe this, it's very cool, it's very white, it's got a lot of blue to it. So when you look at these kinds of contrasting environments, one is warm and one is cool. And this is sort of very common in our design experience when we talk about these interiors. Same thing here. Exactly the same architecture, but it looks very different because one is a very cool environment and one is a very warm environment. As in interior design or interior architecture, we often qualify this as warm colors. We use warm colors in our interior. We also qualify light as a cool color or a cool light. So the design challenge in our world, and when we start looking at the design world, is the challenge here is how do you describe this in some kind of terminology that is common? How can we speak to each other in the design world and talk about cool colors or warm colors? Okay? And so I'm going to talk a little bit more about this in terms of how we actually get into it. And there's two metrics that you're going to be using in your future when you describe architectural interiors. And one is color temperature, and the other is color rendering. Okay? And I'm going to talk about these two concepts before I get into the temples work. So the first concept is what is called correlated color temperature. Okay? And I'm going to get into what this means. In this environment here, exactly the same architecture, but it looks very different because it's using a variety of different color temperatures. And color temperatures are a way of describing relative levels of coolness or warmness. Okay? And this relates predominantly to how our diurnal changes in sunlight. Sunlight can be very warm or it can be very cool. So the design challenge was how do you describe this in terms that you can be prescriptive? How can you put together an architectural specification that says this is how warm something is or this is how cool something is? So the design community many years ago used the analog from the scientific community. And Baron Kelvin developed what was called the Kelvin scale. Okay, and you remember from your science classes, there's the Celsius scale, the Fahrenheit scale, and the Kelvin scale. And Baron Kelvin was not an architect, he was a scientist. Okay? And he developed this Kelvin scale, which was a way of being able to describe the temperature of materials. And so our community, the design artistic community, reached out to the scientific community for a number. They said, we need a number to be able to describe warmness or coolness. So if you take a piece of metal and you start heating it, it starts glowing. And this is, we all know this from our physics classes. And so if you take a piece of metal and you start heating it more and more and more, it goes from a very dull red to yellow to white to blue as you keep putting more energy into it. Okay? So material goes from a very low temperature where it's glowing just very dull red, and then it appears very blue and white. And so, again, this has nothing to do with design. This is just what happens in the physical world. So this is called black body radiation in terms of how materials behave relative to heat. Kind of analogs on this, if you take a candle is just a very dull yellow. It's relatively low temperature, not a lot of energy. But if I take a gas flame and I put a lot of energy into it and make it extremely hot, it glows blue. Okay? So this is showing the range of colors that happen relative to temperature. So color temperature was an analog that the scientific community knows and understands, is that as an object gets hotter and hotter, it goes from red, yellow, white, to blue. And this is how a piece of metal behaves. So the design community said, this is great, this is perfect, because now we can describe warmness or coolness relative to a temperature or an apparent temperature. And this is what is called correlated color temperature. And so if I take this piece of metal and I start heating it up, Kelvin, okay, and I go from 1500 Kelvin to 8000 Kelvin, it looks like a range of different light sources. Okay? And I'll show you an example of this. This is my hometown, San Francisco. And you can see that as the sun is coming up, it's very warm, okay? Very red, low color temperature. So it looks like a piece of metal that's just being heated up a little bit. If I start putting more energy into it, it starts getting red. I put a lot of energy into it, it looks blue. Now, the sky is not that temperature. It looks like it, and this is what correlated color temperature means. So to describe this in more detail, daylight, like today, if we go outside and we measure the correlated color temperature, it's about 8,000 degrees Kelvin. It doesn't mean that the sky is 8,000 Kelvin. It means that it looks like a piece of metal heated to that temperature. This is a ski slope in California, and this daylight is 8,000 Kelvin. It doesn't mean that the sky is that temperature. Now, as the sun starts setting, this is 3,000 Kelvin. It looks like a piece of metal that's heated up to 3,000 Kelvin. It doesn't mean that the sky is that temperature. It means that it sort of looks like that. Candle is about 1,200 Kelvin. The filament lamps that we're all very familiar with, relatively low warm color temperature. The fluorescents that we have in the building here, they can range between 2,700 and 5,000 Kelvin. it doesn't mean that the fluorescent lamps are that temperature. It means that it looks like a piece of metal, like that. And so the way we've been describing this is daylight has a whole range of different color temperatures, all the way from very cool to very warm. Sunsets are typically very low color temperature. Residential environments, very warm. We would call this environment very warm, but we can put a number to it, and that number is 2700 Kelvin. So if I wanted to design an interior like that, I would specify 2700 Kelvin, and that's the number that gets used in design. Residential is typically low color temperature. As a species, we typically prefer lower color temperatures at lower light levels. This is sort of showing a comparison of a kitchen at 2700 Kelvin and a kitchen at 4100 Kelvin. Very different appearance, but if whatever I want, whatever my preference is, I can apply a number to it. Hospitality, hotel design, and this is a lot of my work I do, it's typically very low color temperature. Higher light levels, office environments, laboratories, classrooms, high CCT, high correlated color temperature. In California, United States, it's typically 3500 Kelvin to 4100 Kelvin. In Asia, it's 5000 to 6500, much cooler. Very cool environments for commercial. Very similar to daylight. We would describe this as a very cool interior. Okay? So this is the first design metric that gets used, is correlated color temperature. The next one is color rendering index. Okay? And this is actually very critical for architectural interiors. And the thing to remember about color rendering, it is how good does the candy look? Okay? When I look at this, very saturated color experience. And so color rendering has to do with how good does the red look, how good does the yellow look, how good does the green look. And if you look at this carefully, you can see that the left picture, the face looks a little bit more natural, okay? More red, okay? This is me, okay? So the professor on the left, on this side here, looks anemic. Understand anemic, very, very pale. Okay? The professor on the right, very healthy, red skin, looks good. Okay? This is the concept of naturalness, and that is related to color rendering. And color rendering has to do with the spectrum of the light source. So the concept of naturalness is very central to this. Okay, these two tomatoes. One is under what's 70 CRI, a poor light source, and the other one is on a very good light source. So the red is very saturated, okay? Looks natural. And this has to do with the fact that in order to see red, you need to have a light source that generates red to be reflected, okay? Because overall color experience is driven by whatever the spectrum is, whatever the reflectance characteristics of the material are. So it's very important that you have high color rendering light source. When we describe color rendering, we do that relative to incandescent and daylight. Those are the two standards that get used. Now, why daylight? Daylight is a very broad spectrum. It's rich in all wavelengths. So we tend to use this as the standard when we describe an architectural interior as being good or poor. It's relative to how good daylight is. So the last part I was showing was just the basic terms I'm going to be using: correlated color temperature and color rendering. Okay, and you're going to use these terms in your career. Now I want to talk about my research project, which has to do with Buddhist temples that I've been studying over the last 5 years. And so this morning what I'm going to do is I'm going to talk about some basics on color, I'm going to do sort of a review on how do we see color, what's happening in Buddhist temples, and how is that driving the future of lighting research. And so our whole visual experience, driven by evolution, is that we see a variety of different kinds of spectral distributions throughout the day. In the morning, we see a very red, orange distribution, but it's a very broad spectrum. During the middle of the day, we also see a broad spectrum, but it's very blue. Okay? And so if you look at the color signatures of daylight, it varies considerably. But the one distinguishing feature about daylight, it's always very broad spectrum. There's a lot of different colors in it. We've also had some cultural evolution relative to flame, not biological evolution, but cultural evolution. We're very comfortable with flame light. It also has a very broad spectrum. So if I look at white light, you can take white light and you can split it up into its constituent spectrum. Okay? White light is made up of many colors. Okay? And you're all familiar with the whole concept of the electromagnetic spectrum. It's got a broad range of colors. Now, the thing to understand about light is that there's many different types of spectrum that we're exposed to in architectural design. And the two top spectrum are daylight and incandescent, or flame. And the distinguishing feature here is that it's a continuous broad spectrum. So we've evolved under a very wide spectrum. The bottom spectra are commercial light sources that get used a lot in interiors. And the interesting feature here is that they're discontinuous. They're not smooth and they're not broad, but we use them a lot in architecture. A little bit more detail. The two spectra on the left are what I call natural spectra, incandescent and daylight. They're broad and they're rich. The other spectra are all artificial, ones that we generate inside buildings. And they are characterized as being deficient and discontinuous. Okay? So the process here is, how do we see color when we're inside interiors? And so basic color theory is dependent on what's called the Young-Helmholtz color theory. And this refers to the fact that we see three colors that then are interpreted by our visual system to see all other colors and white light. Okay? So when we see color, we have three sensors that interpret the color world and our interpretation of white light. And this is called the Young-Helmholtz color theory. Okay? So basically, the color signature for our visual system looks something like this. There's blue, green, and red. And when we see different proportions of that, we see different colors. And so we have red cones, blue cones, green cones. And there's a strong bias towards red. We have more red sensors than anything else, and women have even more red sensors than men. So in terms of how we see color, it starts out with what is the spectral sensitivity of the eye? And the eye has a very set spectral sensitivity, except for 10% of the boys who are colorblind. Okay? Then it has to do with what is the spectrum of the light source and what is the nature of the material. So the processes in terms of how we interpret color is first light is reflected off surfaces. That's how we see color. Light is absorbed by materials, or light is transmitted through. And so these are the three primary mechanisms in terms of how we see color. Transmission is pretty easy to understand. As you put white light through colored materials, it selects out or subtracts out different wavelengths, and that's how you see color. However, most of our experience inside buildings is to do with what's called reflection. It's light bouncing off of the surface. So this is typically a subtractive process. Okay? And what do I mean by that? Is that if I have a black surface and I put white light onto it, you absorb all the different wavelengths, and that's why it appears black. If I have a gray surface, the light hits the gray surface, and most of it gets absorbed, but then some of it gets reflected across all wavelengths. That's why it appears gray. A white object receives the white and reflects everything. That's why it appears white. Okay? A red object receives all wavelengths and reflects the red wavelengths, and that's why you see red. Okay? And so there are what are called spectral signatures for color. And so what I'm showing up here is a broad spectrum, and then I'm showing what are called the reflectance characteristics of what blue is, what green is, what black is, what red is. So if somebody wants to describe what does red mean, that's what red means. Okay? Red is that spectral signature. And what it describes is the wavelengths of light that need to be present in order for your eye to see red. So if somebody describes to me, they say, please tell me what red looks like, that's what red looks like in a diagram. Okay? We all like diagrams. We're architects. Right? So again, a red rose, red flower, looks red because broad spectrum gets reflected off of a red signature into our eye.